Subglacial flood erupts from Greenland ice sheet surface, and the eruption of a subglacial flood from the Greenland ice sheet. Introduction. In the last 30 years, the Greenland ice sheet has experienced a staggering loss of approximately 169 billion tons of ice each year, which has contributed around 14 millimeters to the global rise in sea levels. This alarming trend is primarily driven by surface mass balance processes, which account for nearly half of this ice loss, mainly due to increased melting and runoff from the ice surface. As the Arctic continues to warm, predictions indicate that the extent and intensity of surface melting in Greenland will escalate, resulting in even greater ice mass loss and an increase in liquid water, both on and beneath the ice sheet. The importance of meltwater dynamics. Understanding how meltwater travels from its source to the ocean is crucial for evaluating Greenland's future role in sea level rise and its broader effects on the Arctic ecosystem. It is well documented that meltwater produced at the surface of the ice sheet seeps down to the base through features known as moulins and crevasses. Observational studies, particularly in southwestern Greenland, have demonstrated that the subglacial hydrological system reacts swiftly to water input, and fluctuations in subglacial water flow significantly influence the dynamics of the overlying ice. Therefore, it is essential to identify both the nature, whether continuous or episodic, and the pathways, whether surface, englacial or subglacial, of water drainage, as well as how much meltwater is stored during its journey. These elements play a vital role in various processes, including ice dynamics, thermodynamics, interactions between ice and ocean, fjord circulation, primary productivity, and the transfer of sediments and nutrients to the ocean. Subglacial lakes, a new frontier. One of the more recently identified yet poorly understood aspects of Greenland's subglacial hydrological system is its network of active subglacial lakes. These lakes are mainly replenished by surface meltwater that penetrates to the base of the ice sheet and can discharge large volumes of water through the subglacial system when they drain, thereby altering both the morphology of the system and the dynamics of the surrounding ice. However, detailed observations of subglacial lake drainage events in Greenland remain scarce, and our understanding of their causes and effects is still limited. Furthermore, the thermal conditions at the base of the ice, which are crucial for understanding subglacial water distribution and dynamics, remain uncertain across a significant portion of the ice sheet. In light of the increased runoff expected in the 21st century and the anticipated rise in the frequency and extent of subglacial lake drainage, the impacts of these poorly understood events on the ice sheet are still unclear. This study presents observations of a destructive mode of subglacial lake drainage in Greenland and analyzes its effects on the surrounding ice sheet. Observations of subglacial lake drainage in North Greenland. Utilizing high-resolution Arctic DEM digital surface models and satellite imagery, we identified and monitored a previously undetected subglacial lake in northern Greenland, near the marine terminating Harder Glacier. During a 10-day period in the summer of 2014, a 2-kilometer square area of the ice surface experienced an 85-meter drop in elevation, creating a deep collapse basin. This rapid deflation occurred approximately 25 kilometers inland on slow-moving ice adjacent to the main glacier, shortly after the seasonal runoff peak. Prior to this event, the basin surface had been rising, forming a dome about 10 to 15 meters high above the surrounding ice. After the 2014 surface collapse, the ice within the basin began to uplift again, but it subsided by about 10 meters between 2017 and 2019. This dynamic behavior is interpreted as the surface manifestation of an active subglacial lake, akin to those previously documented in Greenland and Antarctica. Estimating water discharge. Assuming that the volume of water released by the subglacial lake corresponds to the volume displaced by the newly formed surface feature, we estimate that approximately 90 million cubic meters of water drained from the lake during the 10-day period. Concurrently, a nearby supraglacial lake also drained, indicating a direct connection between the surface and basal hydrological systems. Modeling of surface and basal melting suggests that the subglacial lake was primarily fed by locally sourced surface meltwater. with over 99% of the water generated within its catchment coming from surface melt, and 73% of all meltwater produced within 2 kilometers of the collapse basin. During the drainage period, the lake discharged water at an average rate of 100 meters cubic per second, with peak discharges likely much higher if the drainage occurred over a shorter time frame. This water flux was 2 orders of magnitude greater than that from a similarly sized Antarctic lake, and represents one of the largest reported events beneath the Greenland ice sheet to date. Notably, the estimated discharge rate indicated a 30-fold increase in the daily meltwater runoff across the entire Harder Glacier catchment at that time, suggesting that the lake drainage significantly disturbed the downstream subglacial system. Surface outburst dynamics. Theoretical models and observations of lake drainage indicate that floodwater is typically routed subglacially, following gradients in hydraulic potential. Thus, subglacial floods in Greenland are generally part of a larger unidirectional hydrological system, where surface meltwater flows from the surface to the bed and eventually to the ocean. However, we have identified evidence of a different drainage pathway. About 1 kilometer downstream from the collapse basin, a new fracture zone appeared in the ice surface, characterized by crevasses and uprooted ice blocks reaching a combined height of 40 meters. Downstream of this fracture zone, an area of approximately 6 square kilometers of the ice surface was scoured clean. These observations suggest that a significant volume of water surged through the ice at this location, flooding across the surface. The hydraulic potential difference between the lake and the fracture site indicates that the floodwater had enough hydraulic head to breach the surface at the fracture site. Notably, estimates of the longitudinal strain rate show a shift from compressional to extensional flow at the fracture site, which may have facilitated the fracturing of the ice column in this area. Historical context of drainage events. Analysis of satellite imagery over the past 36 years reveals that the distinct oval-shaped surface feature above the subglacial lake has been present since at least 1985. Within this time frame, we identified a single drainage event prior to 2014, which occurred between June 21 and August 1, 1990, when the ice was over 10 meters thicker. Unlike the 2014 event, the 1990 drainage did not result in downstream surface fracturing, indicating that the floodwater flowed entirely along the basal interface. Therefore, we conclude that the 2014 surface outburst was unprecedented in the observational record. Impacts of the 2014 outburst on downstream dynamics. The area of ice that was scoured by the flood ended abruptly after several kilometers, at a location where a superglacial lake also drained. The lack of surface scouring beyond this point suggests that the floodwater, after bursting through the ice and flowing across the surface, re-entered the englacial and subglacial systems at this site, continuing its flow beneath the main trunk of the Harder Glacier. The simultaneous drainage of both the subglacial and surface lakes implies that the surface flood may have triggered the latter, likely through hydrofracture at the lake bed. Analysis of the basal hydropotential indicates that the floodwater was subsequently routed beneath the Harder Glacier, exiting at the glacier's main northern terminus. During the same 10-day period, the glacier's terminus experienced a significant calving event with an ice front retreat of 500 to 600 meters, marking the 7th largest event in the past 32 years. While the direct connection to the lake outburst remains uncertain, these observations align with theories suggesting that a rapid influx of water could have influenced the stress regime at the ice front, or enhanced ocean-driven melting and undercutting. Conclusion. Our findings indicate that the drainage of the lake caused a significant disturbance to the hydrological system of the ice sheet. To assess the potential impacts on downstream glacier dynamics, we generated 5,800 maps of ice velocity from 1985 to 2020. These maps reveal that the dynamics of the Harder Glacier exhibit a clear seasonal cycle, superimposed on a longer-term acceleration since 2014-2015. The relationship between lake drainage and the acceleration observed in 2014 remains unclear, given the limited data available prior to 2013 and the multitude of factors influencing the flow of marine terminating glaciers. However, in the weeks following the flood, we observed a notable short-term disturbance in the glacier's dynamics, with a rapid deceleration of 80 meters per year measured approximately 5 kilometers inland from the ice front. While late summer deceleration is typical, the 2014 deceleration was approximately 300% greater than usual, resulting in a 63% loss of peak summer velocity by September 12, compared to an average reduction of 37% in other years. These observations support the theory that a sudden influx of floodwater enhanced the efficiency of the subglacial system, reducing basal water pressures and ultimately slowing ice movement. This mechanism, well established for superglacial lake drainage, appears to also affect fast-flowing, marine-terminating glaciers. Future research directions. Understanding the broader implications of this destructive and poorly understood subglacial flood process necessitates a deeper comprehension of the physical characteristics of the system, including the basal conditions immediately downstream of the lake, which influence the initiation, propagation, and outburst of floods. Although our observations suggest that upward propagating hydrofracture occurred at the outburst site, it remains uncertain whether the drainage of the subglacial lake was also initiated by hydrofracture along the basal interface or through a process associated with temperate ice masses. Further research is needed to explore these hypotheses and to enhance our understanding of the complex interactions within Greenland's hydrological system. Unprecedented flood. 90 billion liters of meltwater breaks through Greenland's ice sheet. In a shocking turn of events, scientists have uncovered a massive flood that burst through the Greenland ice sheet, releasing a staggering 90 billion liters of meltwater. This unprecedented event has left researchers scrambling to understand its implications for the region's melting ice. But here's where it gets controversial. The flood originated from a subglacial lake, a phenomenon that was previously thought to be impossible in Greenland. This discovery has sparked a heated debate among scientists about the role of these hidden lakes in the melting process. The flood, which occurred in 2014, was so powerful that it punched through nearly 91 meters of solid ice, creating a crater that spanned 2 square kilometers and reached depths of 85 meters. The sheer force of the water also fractured a large area of ice downstream, leaving behind ice blocks towering 25 meters high. And this is the part most people miss. This event not only challenges our understanding of how meltwater flows through ice sheets, but it also contradicts existing models that predicted the base of the Greenland ice sheet to be frozen solid. As we delve deeper into this mystery, one thing becomes clear. There is still much we don't know about the complex hydrological system of the Greenland ice sheet. This study has opened up a Pandora's box of questions that scientists are now racing to answer. But here's the kicker. As climate change continues to accelerate, events like this could become more common, potentially leading to catastrophic consequences for the region and the world. The question is, are we prepared to face the reality of a rapidly changing Arctic landscape? What do you think? Is this discovery a wake-up call for the world to take action against climate change? Or is it just another piece of the puzzle in understanding our planet's natural processes? Let us know your thoughts in the comments below. Greenland's surprising ice surge, subglacial flood reveals hidden wonders. A hidden lake in Greenland unleashes a surprising flood of ice. July 30th, 2025, 3-minute read. Water typically flows downward, but an astonishing event occurred beneath Greenland's ice sheet, when a massive surge of water broke through the surface, clearing an area nearly double the size of New York's Central Park. According to a study published in the journal Nature Geoscience, a subglacial flood in Greenland erupted through tens of meters of ice, lifting blocks as large as 5-story buildings and scouring a vast area. This unexpected phenomenon of water shooting upwards rather than flowing down along the base of the ice sheet was described as extremely surprising by Winnie Chu, an assistant professor of geophysics at the Georgia Institute of Technology. Although she was not part of the research team, she studies Greenland's ice and noted that such an event requires some extremely unique conditions for meltwater to force its way up from the bedrock. This remarkable event took place in 2014 near Harder Glacier in the remote northern region of Greenland, where a flash flood would likely go unnoticed. A decade later, Mal Macmillan, a professor of Earth observation at Lancaster University in England, and his team discovered evidence of the flood while analyzing satellite images for sides of lakes hidden beneath the ice. Supporting science journalism. If you find this article engaging, consider supporting our award-winning journalism by subscribing. Your subscription helps ensure the continuation of impactful stories about the discoveries and ideas that shape our world today. These subglacial lakes play a crucial role in influencing the overall water cycle and the movement of ice in Greenland. Typically, they form from surface meltwater that drains down and becomes trapped between the ice and the underlying bedrock. Occasionally, these lakes can drain rapidly, sending water flowing between the ice and rock, sometimes reaching the sea or flowing beneath glaciers, where they facilitate faster glacier movement. However, these lakes are relatively small, making it challenging to accurately account for their effects in models of the Greenland Ice Sheet. Improved satellite imagery has allowed researchers to identify upwellings or depressions in the ice that indicate a subglacial lake is either filling or draining. In examining historical data near Harder Glacier, the research team identified a 2-square-kilometer area of ice that had collapsed into an 85-meter deep sinkhole. We dug deeper into it, and what we found, which was even more interesting, was this fracture zone downstream, which we had totally not expected to see, Macmillan explained. Beyond this fracture zone lay 6 square kilometers of smooth ice, completely cleared by the massive flood. The researchers concluded that the collapsed area was a subglacial lake that had drained rapidly. About a kilometer downstream, however, the water encountered an obstacle. Instead of flowing downward, it surged upward, resulting in the upheaval of ice blocks and crevasses, along with a dramatic release of approximately 90 million cubic meters of water, equivalent to the volume of water that flows over Niagara Falls in 9 hours. This entire event unfolded over a mere 10 days. The water subsequently drained back beneath the ice sheet and may have ended up under Harder Glacier, which coincidentally experienced a significant calving event, where a chunk of ice breaks off and falls into the sea. During the same 10-day period, the glacier also exhibited unusual changes in its flow rate that summer, indicating that the flood likely influenced its dynamics. As reported by the researchers in their recent paper, A Piece of the Ice Puzzle, Robin Bell, a professor of marine and polar geophysics at Columbia University's Lamont Doherty Earth Observatory, who was not involved in the study, remarked, "This is another piece in the puzzle of how large ice formations on our planet operate. The pressing question now is how this new piece fits into the broader narrative of Greenland's rapid warming." Macmillan emphasized the need to investigate whether similar events have occurred in the past. What do you think? Could this phenomenon indicate a larger trend in ice dynamics due to climate change? Share your thoughts in the comments below.